We've learned a lot about force and acceleration, about the cause and effect relationship between the net force and the acceleration it causes. Now we want to try to put together a different cause and effect relationship. Not because it will give us different answers, but just because it's often helpful to have several different ways to approach a problem so that we can select the one that is easiest. So this new approach is going to be in terms of what's called impulse and momentum. So the momentum of an object is the mass of the object multiplied by its velocity. Or we could write it like this, where P stands for momentum, P is equal to mv. So you can see that the momentum is a vector here, and the direction of the momentum is going to be the same as the direction of the velocity. Now, momentum is not just a quantity that describes how the object is moving. Momentum is very much a real substance that is possessed by the object because it's moving. And as we'll see, when objects interact with each other, they can actually transfer momentum back and forth from one to the other. So momentum is a substance that's possessed by the object because it's moving. The impulse is going to be the cause part of our explanation, and the impulse is going to be the average force exerted on something multiplied by the duration of the force, how much time the force is applied. So we could write it like that, where capital J stands for the impulse, and so then we have the average force multiplied by the amount of time the force lasts. So the impulse is also a vector. It's going to point in the same direction as the average force. Now, if you think about how to find the average of something, technically the average is literally found for anything by taking an integral. So this is a more general definition of the impulse. It's the integral of the force integrated versus time from when the force starts until when the force is over with. Or if you want to use the graphical interpretation of an integral, it's also the area under a graph of the force versus time. So what the impulse gives us is it gives us a cumulative effect of the entire event. So impulse is especially useful for looking at situations like collisions, where we have a large, complicated force that lasts for a short amount of time. The impulse gives us a way to add up the cumulative effect of the entire event, as opposed to looking at the force at any one given moment. So let's take a look at an example of just such a situation. So here we have a baseball and a bat colliding. The bat is hitting the baseball. And here we have a graph that might show the force exerted on the baseball by the bat from the moment they make contact until the moment they break contact. So this is a typical sort of force graph that you might get, where the maximum force could be enormous, could be thousands of newtons worth of force. That would be hundreds of pounds of force, but the duration is probably very short, just a fraction of a second. And so the impulse gives us a way to add up the cumulative effect of the entire event by doing that integral. So we have our graph, that's the function f of t, and we would integrate from when the force started to when the force was over. And again, you could also do that by finding the area under the curve like that. Now, if you're going to use the graphical interpretation, you would need to have a very simple graph. If you could find the area just using some simple geometry, then it's probably easier to calculate the area geometrically. On the other hand, if it's a more complicated curving shape, such as the one in the figure here, then it would probably be better to actually do the integral. Either come up with a good equation that approximates the graph you have quite well, or if the computer measured the force versus time, the computer could do the integral for you. But whichever way is easiest to do the integral, either directly or by finding the area, that's going to add up the total effect, if you will, of the entire collision in this case. The alternative, of course, is to find the average force, and that's also possible. If you have computer data, it's often possible for the computer to average the force for you, and then you could simply multiply by the duration of the force itself, and that's the other interpretation of the impulse. They're both entirely equivalent to one another. Now, the other thing to be careful about when you're calculating the impulse is to remember that when you do an integral, it's the area between the axis and the curve is maybe a better way to put it, so that if, as in the figure, the curve is above the t-axis, that would be a positive area, a positive impulse. If you like, the force is positive in the positive direction, so the impulse has to be in that same direction. If you had a curve and the curve was below the t-axis, then that area would technically count as negative. The force would be negative, and so that's the negative direction. The impulse would have to be in the negative direction as well.